Next thing up is colligative properties. Do you guys know what a colligative property is? Have you heard that expression before, colligative properties? Okay. Colligative property is a property of a solution. You only have colligative properties of solutions. A colligative property is a property of a solution that cares only about how crowded it is, how many particles it has in it. It doesn't care what the particles are. So, for example, some classic colligative properties are boiling point elevation, freezing point depression. Things. If I want to cook pasta, I cook pasta for 8 minutes, and I cook it in boiling water. If I do that in San Francisco, the water will boil at 100 degrees Celsius. If I go up to the mountains where the pressure is lower, it'll actually boil less than that. If I cook my pasta for 8 minutes, it'll be raw. How can I make that water boil at a higher temperature so I can consistently use 8 minutes to cook my pasta and still get it cooked? How can I change the boiling point of the water up in the mountains, get it back up to 100 degrees Celsius? I just throw a fistful of salt in there, maybe not a fistful. I put a little bit of salt in there. When you dissolve particles in water, their boiling point goes up. And if I'm in those mountains and I got some snow on my driveway and I want to get it to melt, I might throw that same salt on the ice on my driveway. As the ice melts, it'll dissolve the salt, which will then be rich in salt, and it will have a lower freezing point. Do you ever wonder why the boiling point goes up, but the freezing point goes down when you dissolve these materials in it? Why do when we throw salt in our pasta water, the boiling point goes up, but when we throw it on the driveway, the freezing point goes down? And it's important that you remember these directions, because the formula that you're going to use to calculate this is the same for either one. When you're talking about these colligative properties, freezing point depression, freezing point depression, boiling point elevation, the formula that you're going to use in each case, is just delta T equals your constant. For example, Kb for boiling point, or Kf, it's going to be a different value for freezing point, times the concentration. And like I said, when you're working with different temperatures, you got to use molality. Molality is your go-to for this. The thing is, what you do with that delta T will depend on the property you're working with. If you're working with freezing point, you subtract it from the freezing point of the pure material. Freezing point depression, remember that phrase. And if you're talking about changing the boiling point, whatever you calculate, add it to the boiling point. The boiling point always goes up. But you have to remember the direction. And the way I suggest remembering the direction is just to remember those phrases: boiling point elevation, freezing point depression. All right, these are colligative properties. They care only about the particles you dissolve in solution. By the way, this is why you can use antifreeze in Death Valley, or you can use it in the Sierras. We put it into our radiators when we're in Death Valley to keep the radiator from boiling. We put it into our radiators when we're in the Sierras to keep the radiator from freezing. It does both. All right. Now, like I said, it only cares about the particles, not the nature of the particles. If I have a solution and I throw 10 grams of glucose or 10 grams of sucrose in it, if the freezing point, let's see, if the freezing point, depression, boiling point elevation, In the case of vapor pressure, it reduces the vapor pressure. If in each of these cases, it depends only on the particles and not the substance. If I throw 10 grams of glucose or 10 grams of sucrose into the solution, should it give me the same result? A little bit more information. Glucose is a monosaccharide. It's got 6 carbons, 12 hydrogens, and 6 oxygens. Sucrose is a disaccharide. It's twice as heavy. Would 10 grams of each of these things have the same impact? And if not, which one would have more impact? Which would more significantly change my boiling point, my freezing point, my vapor pressure? Again, it doesn't matter what the particle is. It just depends on how many particles I have in that solution. All right. Notice that we counted these things by mass, right? Which one of these is heavier? Looks like the glucose is the lighter one. It's only got 6 carbons. Sucrose is twice as heavy. So which one of these has more particles in it? 10 grams of the light one or 10 grams of the heavy one? The 10 grams of the heavy one. Yeah, there you go. Now I got it. You're right. 10 grams of the light one would be more particles. And if you go back to that equation that I just gave you, that's what you put here into that's what you put here into the molarity. So if you take 10 grams divided by the molar mass with the light one, you'll have more of those. And it is per kilogram of solvent. So the moles of that divided by the kilograms of the solvent, if that goes up, the change in temperature is going to go up. All right. Now, and again, it only matters how many particles you have, not what they are. Well, kind of. There are some substances that'll play a trick to you. I just told you that it only matters about the particles, not the substance. But with ionic materials, the number of particles you put in per moles of substance is not always 1. If I throw 1 mole of sugar into a solution, I'm throwing 1 mole of sugar particles. But if I throw 1 mole of sodium chloride into solution, I'm throwing in 2 moles of particles. Do you see why? Do you see why I get more particles when I toss in sodium chloride? Karen, did you have a good guess? I think I saw your mic come off there for a minute. What do you think? What's the trick? With ionic materials, when you throw them into solution, they dissociate. So sodium chloride, for example, if I throw, I don't know, 4 moles of sodium chloride in solution, well, then I get 4 moles of sodium and also 4 moles of chloride ion. And again, it only matters about the particles. It doesn't matter what the particles are. Colligative properties like vapor pressure, depression, boiling point, elevation, freezing point, depression, they only care about the number of particles you put in there. So ionic materials can play a trick on you. Now, if I have each of these solutions, which one of these is going to have the highest boiling point? A, B, C, D, E. What do you think? Any guesses? Well, let's see. I know it's not going to be B because B is a molecular substance. So if I have a molality of sugar of 0.05, then my molality of particles is 0.05, and the rest of these are ionic. Oh no, the CO2 is also molecular. CO2 is totally not going to be it. It's not going to be B, it's not going to be D. It could be A, right? Or it could be C, or it could be E. If I throw 0.02 moles of aluminum nitrate in solution, nitrate is, remember, acetates and nitrates, totally soluble. If I put 0.02 molal of aluminum nitrate in solution, what's the molality of my particles in there? Aluminum nitrate, those nitrates are polyatomic particles, and the aluminum's a particle. So if I throw an aluminum nitrate formula unit in there, I get an aluminum ion, a nitrate, and a third nitrate. I get 4. So 0.02 molal in aluminum nitrate is 0.08 in particles. And this equation, that M, that's the number of particles, not the number of, not the moles of substance, the molality of substance, the molality of particles. Now, if I look at the one on the bottom, ammonium chloride, that's going to be less, 0.02 times the Van't Hoff factor, which is how many particles I get. Ammonium chloride, what's the Van't Hoff factor there? Ammonium chloride breaks into how many particles? It's like sodium chloride, breaks into ammonium ion and a chloride ion. Ammonium is one of the polyatomic particles that you're responsible for. It's the only polyatomic cation. So that would be 0.04. C would be 0.08. That's winning so far. But which one of these solutions will give you the most particles? I'm betting on A. Do you see A? Sodium chloride, the Van't Hoff factor is only 2, but it starts with 0.05. So that one's going to be 0.10 molal in sodium chloride. Yeah, Salvador, you got it. Now, when you're working with the ionic materials, you can write this equation differently. And in fact, I suggest you do. Instead of writing it this way, you can say delta T is equal to, for example, KB or KF or whatever you're using, times the molality. But if you don't want to remember that this is the molality of the particles, you can say the molality of the substance times I, where I is the Van't Hoff factor. I is 2 for sodium chloride. I is 4 for aluminum chloride. I is 1 for sugar. It's the number of particles that break apart. Hey, I got a trick for you. You are responsible for only 1 weak electrolyte right now. In 2 more chapters, I'm going to make you responsible for a lot more. We'll talk about electrolytic strength some more when we get there. But do you remember, let's see, HOAC, acetic acid, and HF, hydrogen fluoride? Those are the poster childs for weak electrolytes that we talked about last time. Both of these dissociate only 5% in solution. So for example, HF, if I have 100 particles of HF, when I put it into solution, how many particles are floating around at any given time? Well, I know that the HF, about 95% of it stays as HF. And then I get H plus 5 of it, and I get F minus 5 of it. What's the sum of all that? So if I want to go from 100 to 105, what is my I factor? What am I multiplying it by? You are correct. Van't Hoff factors can be non-integers. In this case, the I for hydrogen fluoride is 1.05. For like ferric chloride, it's like 3.7. For something like lead chloride that doesn't dissolve at all, it's just 1. Okay, but be careful about, in general, if you're given a material and it's an ionic material and you don't know anything more about it, you can assume that it's a strong electrolyte, except for cases where you know otherwise. Like, for example, lead chloride doesn't dissolve at all. Acetic acid and HF, you know, are weak electrolytes, and you're not responsible for knowing they dissociate only 5%, but you are responsible for knowing they don't dissociate 100%. And like I said, in a couple chapters, we will get into more of these weak electrolytes. All right, two more things we need to cover here. One is Raoult's law, and the other is osmotic pressure. Osmotic pressure. Have you guys heard of osmosis before? Do you know what osmosis is? Okay, osmosis is an example. Anyone ever told you water doesn't run uphill? Well, it does. You can make water run uphill. If I take a U-tube like this and I throw, and I put a semi-permeable membrane in between, a filter, which will let water go back and forth, but will block something bigger like a chloride ion. If I throw a fistful of salt in one side, do you know what happens to this? Water runs uphill. There's a pressure. The water will move from one side to the other. Do you know which direction the water moves in? The water is going to move to the higher concentration. That's osmotic pressure. And it's because the sodium chloride particles give water something else to grab onto. So more of the water wants to go to that side. And if the sodium chloride can't come to the water, then the water goes to it. And what happens is water flows uphill. You stack a column of water on one side. This is osmotic pressure, the pressure that's involved in pushing the water to one side. Now, we can use the ideal gas law to quantify that. If you use the ideal gas law, PV equals nRT, you can put a number to that stack of solution. Remember when we were looking at gases, how high a stack of liquids something supports? That's a measure of pressure. So we can look for that pressure by saying N over V RT. All right. Now it's not the pressure that we're used to. So we're going to use a slightly different form of P. We're going to call it pi. That's the symbol we have for osmotic pressure. And this moles per volume, that's just molarity. And then you have RT. Now remember, this is the molarity of particles dissolved in. So let's use the Van't Hoff Factor to make sure we're clear of it. This is the equation for osmotic pressure. And you can use the equation for osmotic pressure to determine how much pressure is applied when the liquid tries to move to the side of the more concentrated material. Here's an example for you. If I have each of these solutions, which one do you think is going to have the greatest osmotic pressure? Which one's going to hold the highest stack of liquid? The sugar, the potassium sulfate, the sodium chloride, or the ferric chloride? I'll give you a hint. It's all about the I factor, the Van't Hoff factor. Which one of these has the biggest Van't Hoff factor and therefore the most particles per kilogram of solution? It's not going to be sugar, right? Sugar's got a Van't Hoff factor of 1. What's the Van't Hoff factor for sodium chloride? That's a question you might see on Monday on the test. Yes, it's 2. So the osmotic pressure is going to be twice what it is for the sugar. It'll have a higher osmotic pressure. How about the potassium sulfate? What's that? What is the Van't Hoff factor for the potassium sulfate? Remember, sulfate's a polyatomic. Yeah, Lisa, you nailed it right. Sulfate sticks together. It's one particle. But then you got a potassium and a potassium. And alkali metals dissolve completely. Remember your solubility rules. So alkali metals, that's got a Van't Hoff factor of like 3. Okay, ferric chloride's a bit of a trick. It's really doesn't have an absolute Van't Hoff factor. But unless you have reason to believe otherwise, treat ionic materials as if they have integer Van't Hoff factors. Be careful, watch your solubility rules, but other than that, ferric chloride, you know, is going to be really soluble in water. And what would the Van't Hoff factor be if ferric chloride had a quantitative or an integer Van't Hoff factor? You got a ferric ion, chloride ion, and a third chloride ion. What's the Van't Hoff factor? Nailed it. Salvador, you got it. Like I say, ferric chloride's actually a little bit less than that, but it's close enough, for at least for this one. I'm just asking which one's the biggest. 1, 2, 3, or almost 4. And it's the ferric chloride. Be careful about your solubility rules when you're looking at these. But other than that, you're good to go. Okay. Now, just to give you some context for osmotic pressure, osmotic pressure is not just about plumbing and you know, irrigation. It's a biological factor too. You ever hear the saying that your electrolytes are off? What they're talking about is the material dissolved in your blood versus the material dissolved in blood cells, for example. Now, if you don't have enough electrolytes in your blood, the pressure will cause your blood cells to expand. And if you've got too much salt in your blood, if you're pounding like the Gatorade and you're putting too much salt in, then you've got more salts dissolved in your blood, and it'll suck all of the liquid out of the blood cells, and it'll actually cause them to collapse. So this is this osmotic pressure thing has real implications, not just in plumbing, but also in biology. All right, the last thing up is vapor pressure. We need to talk about vapor pressure. And I know I'm about 4 minutes over time, but I'm just going to keep going. And if you guys want to hang with me, that's cool. If you need to go, that's cool too. But let's talk about vapor pressure. I told you vapor pressure is also a colligative property, and it is. More accurately, vapor pressure depression. When you throw salt into a solution, it makes it harder for the volatile materials in that solution to escape. They have something new to hang on to. So, for example, if I have two solutions, you can win a bar bet with this. Walk into a bar, tell someone to put 2 glasses of water on the bar, and say, "I tell you what, I can move all the water from one glass into the other without touching either glass. You buy me a drink if I can make that happen?" If they'll buy you a drink just to get you to answer the question. They want to know how the trick is done. The way the trick is done is you throw a fistful of salt in one glass. Don't touch the glass, just drop the salt in it. And then put a bell jar over the top. And yeah, you got to wait 2 weeks for this to work, but you can. But if you explain it to them, they'll probably buy you a drink the same day. Which one of these do you think has the lower vapor pressure? In other words, is going to have the water. See, hypertonic one would be related to sickle cell anemia. I think sickle cell anemia is actually a distortion of the cell structure. I don't think it's caused by pressure, but I'm not a biologist, so I'm not 100% sure. I could bug my wife about it. She's a microbiologist, but I'm uncertain about that one. But that's a great question, and that is anemia in general is a big problem. As we remember, blood cells are how we get oxygen around our body. Do you know that you could suffocate in a room full of oxygen? You could, because if it doesn't matter about how much oxygen gets to your lungs, it matters how much oxygen gets to your muscles and your organs. And the blood cells are the things that move them. So if you're anemic enough, you could suffocate. You could run out of oxygen in a room full of oxygen. By the way, that's how like cyanide poison works. Cyanide binds to the blood cells and won't let the oxygen in. All right. But in this case, which one do you think has the higher vapor pressure? In other words, the vapor is coming off of it more. The pure solvent or the concentrated solution? Which one is the higher vapor pressure? See, vapor pressure, when I throw salt into it, does the vapor pressure go up or down? I mean, the freezing point goes down. The boiling point goes up. What happens to the vapor pressure when I throw a fistful of salt in it? For the same reason, the boiling point goes up, because I've now given the solvent something to grab onto. The vapor pressure goes down. So vapor pressure and boiling point, it's actually the same phenomena, but the two numbers move in opposite directions. Vapor pressure is reduced. So the concentrated solution is going to have a lower vapor pressure. The other one's going to keep kicking it out. And if you leave this there for 2 weeks, literally all the water will go from the pure solvent glass to the other one that gal buy you a drink in the bar. The kinds of problems that you're going to run into with this, you will use Raoult's law. Let's see, do you know Raoult's law? Have you guys played with Raoult's law? Probably not. We don't usually introduce Raoult's law prior to this. So Raoult's law is probably something new to you. Raoult's law is a way of calculating vapor pressure. You can get the vapor pressure of a solution, the vapor pressure of some volatile component. And it could be the solvent, it could be a volatile solute, doesn't really matter. For example, the vapor pressure of H2O, it relates the vapor pressure of H2O to the vapor in solution to the vapor pressure of H2O pure. And it does it by a concentration factor. Okay, so we've used molarity, we've used molality. What's the third big measure of concentration? The one we use for gases, and this is a gas. Do you remember the other one? Yeah, mole fraction, you got it. So the mole fraction, and you got to be careful here, the mole fraction of the water. This is Raoult's law, okay? So I can get the vapor pressure of any component in a solution, any volatile component, any component that has a vapor pressure. Water could be a solute. I could have benzene dissolved in water, and I could get the vapor pressure of the water and the vapor pressure of the benzene. I just have to find the mole fraction and multiply it by the original vapor pressure. So what is mole fraction? How do you calculate mole fraction? What is mole fraction? Is moles of solute over, because they're all moles of solute over, or moles of whatever I'm looking at. Water here could be the solvent, over moles of, I gave it away, over moles of solution. So it's one is kilograms of solvent, the other is liters of solution, and for mole fraction, it's moles of solution. So it'd be moles of water over moles of water plus, say, moles of benzene. And Raoult's law is kind of neat. If you use Raoult's law to calculate, the vapor pressure, you'll see that as you change the mixture of something from like pure water to a mixture, Raoult's law will is just a straight line. It's just a linear relationship. And the same way, if you start with 0 of this other thing and go up, Raoult's law will give you a straight line. Now, here's the thing. This Raoult's law is based on, Dalton's law is based on the ideal gas law, which is based on KMT. So this is true of something that is an ideal gas. And while the ideal gas law is good to about 3 sig figs for most real gases, it's not as good in Raoult's law. You will see deviation of the two of these. You'll see deviation of the two of these where with real gases. Now it's based on the solute-solvent interaction. Basically, it's a straight line as long as the interactions between the solute and the solvent, the adhesive intermolecular forces, are the same or on the same order as the one between solute-solute and between solvent-solvent. But if the solute-solvent ones are weaker, what do you think happens to the vapor pressure? If that stuff that I'm adding that is holding the other thing in solution gets weaker, what do you think is going to happen to the vapor pressure if the solute-solvent interactions are weaker than the ones within solute, within solvent? Yeah, it's going to go up, right? So you'll see a curve that kind of looks like this for a real substance where the adhesive interactions are weaker. And you can have a situation where they're actually stronger. And then the vapor pressure is even less. The curves look like this. Okay. All right, so this is Raoult's law. A solution that obeys Raoult's law is cool. You can do a lot of stuff with this. When a solution obeys Raoult's law perfectly, we call it an ideal solution. But most solutions are not ideal. Either the interactions are stronger, like say acetone water, or they are weaker, like say benzene hexane, in which case you get one of these two deviations. The last thing that we should talk about is colloids. We're not going to do much with regard to colloids. You don't need a whole lot of this. You just need to know what colloids are. Colloids occur. Well, so we've been talking about solutions all along. Solutions are a homogeneous mixture. And you know, heterogeneous mixtures are when you have phases. Well, there's a gray area in between, and that's a colloid. Colloids are solutions where the particles are different enough in size that it doesn't really form a separate phase, but it gets kind of hazy. Colloids are identifiable by the cutoff line here. As you start mixing things of different sizes, like milk is a colloid, but if you have really thin milk, it's transparent, but it's hazy. And as you mix more, as the concentration goes up, it actually gets opaque. But when you have these solutions like salt water, sometimes you'll get plankton or stuff in salt water. They're much bigger particles in the water. It's kind of a solution that looks homogeneous, but it gets really hazy. If you want to find out if it crossed the line, if it became a colloid or not, use the Tyndall effect. The Tyndall effect is shine a light through this transparent material. If the light just goes through and you don't see anything, you call it a solution. If the Tyndall effect doesn't appear, it's a solution. It's a homogeneous mixture. But if the particle sizes are different enough, you will get light scattering as the light going through the solution bounces off the bigger particles. You'll literally see like a beam of light in there. If you see the Tyndall effect, we're in this gray zone between heterogeneous and homogeneous that is a colloid. Now, colloids have some additional consequences to them. You're not entirely responsible for them. I think the only piece that you are responsible for knowing is what is a colloid. If you take biology, you'll be using this, and they may ask you, "What is a colloid?" Well, now you know. And the Tyndall effect, the experiment by which we demonstrate something as a colloid. Okay, that's it for chapter 14. That's all the stuff we got for you. Any questions on any of this stuff? Are you comfortable? You ready for that block test on Monday? Or actually, it's going to open probably like Saturday night. So you could dive in Saturday. I would take it on Sunday when you got a little bit extra time. But it's good through Monday. So if you want to take it Monday night, that works too. Any questions on any of this stuff? You all good? Okay. All right. Appreciate you sitting through that. That was a long-winded thing. I just wanted to make sure I hit all the high points for you. I'll let you guys go then, and I hope you have a great weekend. Oh, by the way, lab thing. As a reminder, if you weren't able to pick up the lab kit this week, I've extended the due date. They sold out the lab kit. They're getting some more in, but it didn't come in on Thursday like it was supposed to. It's going to land on Monday. So if you don't have the lab kit, make sure you reserve one. It might be too late to do it now, but make sure you reserve a lab kit. They're getting a bunch in on Monday, and they probably will sell out again. So I would hit them early on Monday to get that lab kit. All right. If there's nothing else, I'm gonna let you guys go. I'm gonna call it a night in the week, and good luck on the test.
Professor?
Yeah, go for it.
Yeah, I'm sorry, I couldn't join the whole day, the whole hour. I
No
have a
worries.
family thing going. Um, are you able to extend the homework? I wasn't able to finish it.
Yeah, not a problem. Uh, in fact, I think I may already have done that. If it gets marked late, no worries.
Hmm.
If it shouldn't remove anything, but if it does, I'll credit it back when I transfer it over to Canvas. So if you need a little bit more time on the homework, that is not a problem.
Okay. I wasn't able to we weren't able to do the two questions from the last quiz, but maybe we can do it
Um,
on Monday or I mean Wednesday.
yeah, that's totally fine. If you want to ask some questions on that quiz, although with the block test coming up, if you want to ask those questions qualitatively right now, I don't mind hanging around a little bit longer.
Oh, okay. It was question 10 and 12.
Okay, just kind of paraphrase it for me. What were they asking for in 10?
Oh, I don't have it open right now.
Okay, do you mind if I share that with other folks? Is that okay to do?
Sure, that's fine. Thank you.
All right. Let me see if I can pull it up here. Let's see. You said 10 and 12, and that would have been, what week are we in here? We're in week 3, so that would have been quiz 2. So pulling up quiz 2, and then let me find yours here. And I got a lot of students this semester. Okay, here we go. There we go. And let me just scroll down to the ones we're talking about. Looks like 10. Okay. So here's question 10. And it looks like what they're asking you, they say commercial grade HCl solutions are typically 39% by mass HCl in water. Determine the molality of the HCl if the solution has a density of 1.20 grams. Oh, that's literally one of the ones we did today, I think. So the way you would do this, let me see how you would do this. You would start by assuming some mass. So you assume like 100 milliliters or 100 grams. If you start with 100 grams, that means you got 39 grams of HCl and you got 61 grams of water. Now, let's see. Oh, this is going the other direction. How many mole? Oh no, this is going there at molality. So you want to know the you want to know. Oh, this one's easier than the one we did actually. No. Okay, so if they give you 39% grams, just assume you have say 100 grams of solution. If I have 100 grams of solution, it's 39% HCl, then 39 grams of HCl. You good going from grams to moles for HCl? Chlorine is just like 35.45 molar mass, hydrogen's 1.008, it's like 36. So you take 39 basically divided by 36, that'll give you the moles of HCl. Make sense?
Yeah.
Okay. So you got the moles of HCl then. Then you say, okay, well, I got moles of HCl and I need to divide it by kilograms of solvent. Well, if it's 39% HCl in water, then it's 61 grams of water. So all I got to do is take that like 36 and divide it by, here, let me crunch this number.
You said take 36. What is 36 from?
Oh, no, I misspoke. So 36 is 36 is the molar mass of HCl. So you take 39 grams and you divide it by 39 grams and divide it by about 36 grams per mole, because that's the molar mass of HCl. Remember, chlorine is 35.45, hydrogen is 1. So it's like 36 and a half is about the molar mass of HCl. So I'm taking 39 grams of HCl and dividing by the molar mass. I get something like about 1.08. So that tells me the molarity of this is about 1.08. And then I divide that by 0.061. 0.061 is basically 61 grams of water turned into kilograms. So 0.061 kilograms. So I take 1.08 and I divide it by 0.061. I don't know, I get something like about 17.8, which, since I've been rounding off numbers, well, the only one that really fits is that 17.5. Did that process make sense to you?
Yes.
Okay. So you don't even need the density. Density isn't even involved in this one. Probably they created like 3 or 4 questions and they asked you different things about it. And maybe for some of the other things, you need the density. If you retake the quiz, the question may be different. You may get the same one, but it may be different. So read the question carefully. But in general, here's the important things to remember. Molality is moles of solute per kilograms of solvent. The mass percent is just literally what it sounds like. And when you're looking at these things, if all of the properties there are intensive properties, like density and mass percent, any concentration is an intensive property. You need some kind of extensive property. So just assume some quantity. 100 grams, 1 liter, 1 kilogram. Just assume that and then scale off it. And that will give you a concrete reference to get out the missing property. So when stuck, just say, well, just right across the top of the paper, I assume 100 grams or 100 milliliters and then go from there. Are you good on this one? Is this making sense? Did I go too fast?
Yeah. So the density given here is kind of like bogus for this particular problem.
Yeah.
Or you can use the volume formula and then find the mass and go from there, but it's more complicated, right?
So I would try and make it more complicated here. So, I mean, basically what I'd do is if they gave me this one, here. The first thing I would do is I'd say, okay, assume 100.00 grams. And then if it's 39% HCl in water by mass, then by definition, that's going to be 39 grams of HCl, which if you divide it by 1 mole over 36.5 grams, which is the molar mass of HCl, you're going to get something like 1.08 moles of HCl. And molality is just moles of the solute over kilograms of the solvent. So this is going to go right here. And now all I need is the mass of the solvent. Well, they told me it's 61 grams of water because they told me it's 39% HCl in water. So it's 39 grams of this, it's 61 grams of this. If I want to make that kilograms, I just put a killi on the top, 10 to the minus 3 on the bottom. That gives me 0.061 kilograms of water. That's what goes on the bottom. So this number divided by this number And when I just crunched it, I got like 17.8, which, like I said, I was sloppy with my numbers. But I bet that's clearly the one that they got left, which is oops, wrong one. Which is this one.
I think it was 17.5.
Yeah, 17.5. I got 17.8, but I'm playing fast and loose with the numbers here. But that's enough to indicate that it's not going to be the 9 or the 6 or the 39. So that's good enough to put a circle around it. Bob's your uncle. You're done. Make sense?
Yes, thank you.
All right. You said 12 too. Let's take a look at 12. Determine the vapor pressure of a solution that's 25 degrees Celsius that contains 76.6 grams of glucose in 200 ml of water. Vapor pressure of pure water. This is just Raoult's law. Okay, so Raoult's law is basically Raoult's law is cool. Raoult's law says that if I want to have the vapor pressure of anything that's in the solution, it could be a solvent, it could be a solute, it doesn't matter. But if I want to have the vapor pressure of something in solution, in this case, let's see, what is it they were asking for the vapor pressure of? I'm guessing it's water. So they're asking for the vapor pressure of water. So if they want the vapor pressure of water in this solution, it's just the vapor pressure of pure water times the mole fraction of, and this is where you got to be careful, the mole fraction of the water. Okay. It'll be easier to calculate the mole fraction of the solute, but you're going to have to go backwards from that. You want the vapor pressure of the water in that. So if you go over here, well, they gave you the pure vapor pressure, 23.2. So you just need to multiply that by the mole fraction of water. Okay, so how do you do that? Let's see. Determine the vapor pressure of 23.6 in 250 mils of water. Okay. So 250 mils of water is 250 grams of water. Because remember, water has a density of 1. That's literally the 0 point in our density scale. So at least at 25 degrees Celsius is the density of 1. So 25 mils means 25 grams. Take 25 grams of water divided by 18.02. That's the molar mass of water. Always have your periodic table handy. And that'll give you the moles of water. Do the same thing with moles of glucose. Then put moles of water over moles of water plus glucose and multiply that by 23.8. You're done. Make sense?
Yes.
All right. And I'm doing this fast and loose here, but on a test or something, take your time. You should have plenty of time on these tests. Write it out on a piece of paper and give yourself plenty of space. You know, be casual with paper. I am a tree's worst enemy when I take a test. I burn up paper right and left. But I like to think that the trees win to a good cause by giving myself lots of space on the paper. I'm less likely to make silly mistakes. If you crowd yourself in, you're more likely to leave something out or do something silly. So just give yourself plenty of space. You should have plenty of time on these tests. Take it slow, and you'll be fine. You'll be fine.
Thank you, Professor. So did you extend for the time for the next quiz?
Yeah, I was talking with someone else. I'm just going to bump up the time across the board on this because some other folks were getting crowded too. And especially for a block test, I want to make sure you guys have plenty of time. So I will bump up the time. Hopefully it'll be way more time than you need because, man, I couldn't sit in front of it. It already gives you like 2 hours. And I would not sit in front of a computer for I would sit in front of a computer for 2 hours. But I'll bump up the time. So the time shouldn't even be on your map. Just take your time, focus on the problems, you'll be fine.
Okay, thank you, Professor.
You're welcome. All right, folks, I'm going to call it a night here. I got to get I got to get a little bit of food in my stomach. I'm actually starving here, but I will let you guys go.
Thank you so much. You have a great weekend.
You too. Bye-bye.
Bye bye.